Welcome! Today, we'll dive into an exciting problem from LeetCode, number 1569, number of ways to reorder array to get same BST. In this problem, we'll explore how to determine the number of ways to reorder an array such that it results in the same binary search tree. Let's get started. In this problem, you are given an array called nums, which is a permutation of integers from 1 to n. Using this array, we can construct a binary search tree, or BST, by inserting the elements into an empty tree in the order they appear in nums. The first element in the array becomes the root of the tree, and each subsequent element is inserted according to the BST property. If the current element is smaller than the value at the current node, it goes to the left subtree, otherwise, it goes to the right subtree. Your task is to find all the possible ways to reorder the array nums such that, when we build the BST using that reordered array, the structure of the BST remains identical to the one built from the original order of nums. Since the number of reorders can be very large, the result should be returned modulo 10 to the power of 9 plus 7. The input to the problem is the array nums, and it will contain integers from 1 to n with no duplicates. The output of this problem is a single integer. This integer represents the number of ways to reorder the array nums such that the binary search tree built from the reordered array is structurally identical to the BST built from the original array. You must return this result modulo 10 to the power of 9 plus 7. Let's look at some examples to better understand the problem. First, consider the input nums equals 2, 1, 3. If we construct the BST from this array, we start with 2 as the root. Next, 1 is inserted into the left subtree because it's smaller than 2, and 3 is inserted into the right subtree because it's larger than 2. The resulting BST looks like this: 2 at the root, with 1 as its left child and 3 as its right child. In this example, there is only one way to reorder the array nums while maintaining the same BST structure, and that is to keep the array as 2, 1, 3. Any other permutation, such as 1, 2, 3, or 3, 2, 1, would result in a different BST structure. For instance, 1, 2, 3 would create a BST with 1 as the root, which is not the same as the original tree. Now, let's look at a larger example: nums equals 3, 4, 5, 1, 2. When we build the BST, 3 is the root. 4 is inserted to the right of 3, 5 to the right of 4, and then we insert 1 into the left subtree of 3, followed by 2 into the right subtree of 1. This creates a BST that is slightly more complex, with 3 as the root, a deep right subtree, and a smaller left subtree under 1. For the array nums equals 3, 4, 5, 1, 2, there are 5 different ways to reorder the array while preserving the structure of the original BST. For example, one valid reorder is 3, 4, 1, 5, 2. Here, the relative positions of elements within the left and right subtrees of the original BST are preserved. Another valid reorder is 3, 1, 4, 5, 2. Similarly, reorders like 3, 1, 4, 2, 5, and 3, 4, 1, 2, 5 also produce the same BST. Finally, the original order, 3, 4, 5, 1, 2, itself is one of the valid reorders. However, for certain inputs, it may not be possible to reorder the array at all without altering the BST structure. Consider the input nums equals 1, 2, 3. Here, the BST is constructed with 1 as the root, 2 as the right child of 1, and 3 as the right child of 2. This creates a BST that is essentially a straight line. In this case, there is no way to reorder the array nums to produce the same BST structure, except by keeping the original order, 1, 2, 3. Any other permutation will change the sequence of insertions, resulting in a different BST. For instance, swapping the positions of any two elements would introduce left subtrees or alter the depth of the nodes, breaking the original structure. Therefore, the output for this example is 0. To summarize, when the array nums has only one element, such as nums equals 1, there is only one possible BST, and the result is always 1. For larger arrays, the challenge lies in efficiently counting all valid reorders when the input size can go up to 1000. This requires handling very large combinations and applying modular arithmetic to avoid overflow. It's important to adhere to the strict BST insertion rules, as even a small change in the order can create a completely different tree. A key observation is that any valid reorder must preserve the relative positions of elements in the left and right subtrees. By combining combinatorics and a divide-and-conquer approach, we can recursively count these valid reorderings and solve the problem efficiently. To solve the problem of finding the number of ways to reorder an array to produce the same BST, we first consider a brute force approach. This method involves generating all possible permutations of the input array and constructing a BST for each permutation. By comparing these BSTs to the original one, we can count the valid reorderings. While the concept is straightforward, this approach quickly becomes impractical due to its factorial time complexity, O(n), as the number of permutations grows explosively with the size of the array. On the other hand, an optimized approach takes advantage of the inherent properties of binary search trees. For instance, in any BST, nodes in the left subtree are always smaller than the root, while nodes in the right subtree are larger. This insight allows us to focus only on the relative order of elements rather than generating all permutations. Using a divide-and-conquer strategy, we can recursively split the problem into smaller subproblems, constructing the left and right subtrees independently based on the root and then combining these results efficiently. A key part of the optimized approach involves leveraging combinatorics to calculate how different subtrees can be interleaved while maintaining their internal order. Specifically, we use combinations to determine the number of ways to merge the left and right subtrees. The formula for combinations, CM(k), computes the number of ways to choose k elements from a total of m, and it is given by m divided by the product of k and mk. Here, m represents the total number of elements, while k represents the size of one subtree. With this insight, the chosen strategy combines recursive decomposition with pre-computed combinatorial values to efficiently calculate the valid reorderings. Each recursive step involves splitting the array into left and right subtrees, counting the ways to interleave these subtrees, and recursively processing each subtree. To speed up these calculations, factorials are pre-computed up to the size of the array. This ensures that combination values can be derived in constant time. Additionally, results are computed modulo 10 to the power of 9 plus 7 to handle potential integer overflow and to meet problem constraints. The time complexity of this approach is O(n squared, driven by the need to split the array at each recursive step. The space complexity is O(n), which accounts for the recursion stack. This strategy was chosen because it balances computational efficiency with clarity. It avoids the exponential time complexity of the brute force method by leveraging the structural properties of BSTs. The divide-and-conquer approach aligns naturally with the recursive nature of the problem, while pre-computing factorials reduces redundant calculations. However, there are trade-offs. For example, while brute force is easier to conceptualize, it is computationally infeasible for large arrays. Recursion, while elegant, uses additional stack space, which an iterative approach could potentially avoid, though at the cost of implementation complexity. Pre-computing factorials adds an upfront cost but significantly accelerates the main computation. The critical insight, or aha moment, lies in recognizing that the problem can be reduced to counting interleavings of two subtrees while preserving their internal order. Combining this with pre-computed combinatorics transforms an intractable problem into one that is solvable in quadratic time. To tackle this problem, we start by understanding the core task, determining how many permutations of the array result in constructing the same binary search tree, or BST. A BST is built by inserting elements one at a time into an empty tree, with smaller values going to the left and larger values to the right. The brute force approach begins with generating all possible permutations of the given array nums. Using a method like backtracking, we can explore every possible arrangement of elements. For an array of size n, this will produce n permutations. Once we have these permutations, the next step is to construct the BST for each one. By sequentially inserting elements from the permutation into an initially empty tree, we simulate the BST construction process. A helper function ensures that each value is placed correctly based on the BST rules. Although this approach is straightforward, it's computationally expensive. However, it provides clarity on how the problem can be solved systematically and lays the foundation for understanding optimization techniques later on. After constructing the BST for each permutation, the next step is to compare their structures. To do this efficiently, we convert each constructed BST into a serialized format, such as a string representation of its pre-order traversal. This conversion makes it easier to compare the structure of trees. We first serialize the BST created from the original array nums to establish the reference structure. Then, for each permutation, we serialize its resulting BST and compare it to the reference. If the serialized structures match, that permutation is considered valid because it produces the same BST as the reference. Finally, we count all valid permutations and return this count. The key insight here is that two BSTs are considered equal if they share the same structure in node values, and since the array contains unique values, we only need to compare their structures. It's important to note that this brute force method, while simple and guaranteed to work for small inputs, is computationally expensive due to the factorial growth of permutations. It serves as a baseline for understanding and validating more efficient algorithms. To implement the algorithm, we rely on a few essential data structures. Each node in the BST contains a value and pointers to its left and right children, enabling efficient insertion and traversal. The permutations of the array are stored in a list, which we iterate over to construct BSTs sequentially. To facilitate the comparison of BST structures, we use a hash map or set to store their serialized forms. This helps in quickly checking whether two BSTs are structurally identical. As we move toward optimization, one strategy is to prune invalid permutations early. For example, by monitoring the order of left and right insertions during BST construction, we can avoid exploring permutations that cannot match the reference structure. Another powerful approach is to use dynamic programming to compute the number of valid permutations directly. By analyzing the relative positions of elements, we can bypass the need to explicitly generate all permutations. These optimizations significantly reduce computational overhead while maintaining correctness. Finally, let's analyze the complexity of the brute force approach. Generating all permutations of the array takes n. As there are n possible arrangements. Constructing the BST for each permutation involves inserting n elements, which takes n per permutation, leading to a total of n. *n, operations for tree construction. Comparing the BST structures also takes n per comparison, adding another n. *n to the total. Thus, the overall time complexity of this approach is n. *n. Spacewise, constructing a BST requires n memory for the tree itself, while storing all permutations requires n space. Therefore, the total space complexity is n plus n. While this brute force method is computationally intensive, it provides a clear understanding of the problem and can be used to verify results from more efficient algorithms. By exploring optimizations like pruning and dynamic programming, we can significantly reduce both time and space requirements for larger input sizes. This code solves the problem of finding the number of ways to reorder an array to get the same binary search tree, BST. The key insight is that the structure of a BST depends only on the relative order of elements, not the exact order. The solution uses recursion and combinatorics. First, we define a recursive function count_ways that calculates the number of valid reorderings for a given array. If the array has two or fewer elements, it cannot be reordered, so the function returns 1. Otherwise, the first element is treated as the root, and the array is divided into left and right subarrays based on whether elements are smaller or larger than the root. This division maintains the BST properties. The number of ways to interleave the left and right subarrays is given by the binomial coefficient comm, len, left, plus len, right, len, left. This represents how many ways we can choose positions for the left subarray elements among the total elements. We recursively compute the number of ways to reorder the left and right subarrays and multiply these with the interleaving count to get the overall count for the current array. The result is adjusted by subtracting 1 because the original order of the array is not considered a valid reordering. Finally, the result is returned modulo 10 to the power of 9 plus 7 to handle large numbers. The function uses a helper comm from Python's math module to compute combinations efficiently. The solution is optimized for clarity and correctness, avoiding unnecessary complexity. The algorithm handles edge cases such as small arrays and ensures modular arithmetic throughout to prevent overflow. Here, we begin by importing the necessary packages and defining the solution class. We also declare a constant mod to handle large numbers and avoid overflow when performing modular arithmetic. The main method, number of ways, takes an array of integers called nums, which represents the sequence of nodes in the binary search tree. First, we initialize a 2D array called com to store pre-computed combinations using Pascal's triangle. This is done to optimize the process of calculating combinations later. Each value in com, I, j, represents the number of ways to pick j elements from a set of I elements. By iterating through the rows and columns of this array, we fill in the values using the formula derived from Pascal's triangle, taking care to apply the modulo operation to keep the values within range. After pre-computing the combinations, we call a helper function, countways, passing nums and the com array. The result is adjusted by subtracting 1 to exclude the original ordering, ensuring the modulo operation keeps the result positive, and then we return it as an integer. Now, in the recursive countways method, we first handle the base case. If the input array nums has 2 or fewer elements, there is only one way to form the BST, so we return 1. For larger arrays, we take the first element, nums, 0, as the root of the tree. Using this root, we partition the remaining elements into 2 lists, left for elements smaller than the root and right for elements greater than or equal to the root. This is achieved through a simple loop that iterates over the array. Once the left and right subtrees are identified, we recursively compute the number of ways to arrange the left and right subtrees using the same countways method. Finally, we calculate the number of ways to interleave the left and right subtrees while maintaining their relative order. This is done using the pre-computed combinations, where com, left.size, plus right.size, left.size, gives the number of ways to arrange the left and right subtrees. We multiply this value with the results of the recursive calls for the left and right subtrees, applying the modulo operation at each step to ensure the result remains manageable. This value is then returned to contribute to the final count. We start with the array nums equals 2, 1, 3. The first step is to call the function count_ways, nums. Since the array length is greater than 2, we proceed to establish the root of the current binary search tree as the first element of the array, which is 2. Next, we split the array into 2 parts, the left subtree, containing elements less than 2, which gives us 1, and the right subtree, containing elements greater than 2, which gives us 3. Now, we recursively compute the number of reorderings for each of these subtrees. For left equals 1, since its length is less than or equal to 2, we hit the base case and return 1. Similarly, for right equals 3, the base case applies, and we return 1 as well. After completing the recursive calls, we calculate the combinations for arranging the nodes. The total number of nodes in the left and right subtrees is 1 plus 1 equals 2. To determine the number of ways we can position the left subtree nodes relative to the right subtree nodes, we compute com, 2, 1, which equals 2. Next, we multiply this result by the counts returned from the recursive calls. So, the total number of ways becomes 2 * 1 * 1 equals 2. However, we need to subtract 1 from this result because the original ordering of the array does not count as a valid reordering. This gives us 2, 1 equals 1. Therefore, the final result for this example is 1. Moving on to nums equals 3, 1, 4, 2, we start by calling count_ways, nums. In the second example, the array length is greater than 2, so we proceed. The root of the BST is the first element, 3. We split the array into left equals 1, 2, for elements less than 3 and right equals 4, for elements greater than 3. Now, we recursively compute the number of reorderings for each subtree. For left equals 1, 2, we identify 1 as the root. Splitting further, the left subtree becomes, and the right subtree is, 2. For the empty left subtree, the base case applies, so we return 1. Similarly, for the right subtree, 2, the base case applies, and we return 1. Combining these results, we compute com, 1, 0, * 1 * 1 equals 1. For right equals 4, the base case applies, and we return 1. Now, we calculate the total combinations for the left and right subtrees of the root 3. the total number of nodes in these subtrees is 2 plus 1 equals 3. To determine the number of ways to position the left subtree nodes relative to the right subtree nodes, we compute COM, 3, 2, which equals 3. Multiplying this by the results of the recursive calls, we get 3 asterisk 1 asterisk 1 equals 3. Finally, we subtract 1 to exclude the original ordering, resulting in 3, 1 equals 2. Thus, the total number of valid reorderings for this example is 2. Now, let's consider the next array, nums equals 5, 3, 8, 2, 4, 7, 9, where we begin the process by calling count_ways, nums. For this larger example, the array length is greater than 2, so we proceed. The root of the BST is the first element, 5. Splitting the array, we get left equals 3, 2, 4 for elements less than 5 and right equals 8, 7, 9 for elements greater than 5. We now recursively compute the number of reorderings for these subtrees. For left equals 3, 2, 4, the root is 3, which splits into left equals 2, and right equals 4. Both 2 and 4 hit the base case, so we return 1 for each. Combining these results, we compute COM, 2, 1, asterisk 1 asterisk 1 equals 2. Similarly, for right equals 8, 7, 9, the root is 8, which splits into left equals 7, and right equals 9. Again, both subtrees hit the base case, so we return 1 for each. Combining these, we compute COM, 2, 1, asterisk 1 asterisk 1 equals 2. Finally, we calculate the total combinations for the left and right subtrees of the root 5. The total number of nodes in these subtrees is 3 plus 3 equals 6. To determine the number of ways to position the left subtree nodes relative to the right subtree nodes, we compute COM, 6, 3, which equals 20. Multiplying this by the results of the recursive calls, we get 20 asterisk 2 asterisk 2 equals 80. As before, we subtract 1 to exclude the original ordering, resulting in 81 equals 79. Thus, the total number of valid reorderings for this example is 79. This completes the computation for the given examples of the problem. To analyze the time complexity of our solution, we start by examining the recursive function count_ways. One key operation within this function is the recursive splitting of the array. At each step, the array is divided into two subarrays, left, containing elements smaller than the root, and right, containing elements larger than the root. This process requires iterating through the array to partition it, which takes n time for an array of size n. Additionally, there is the combination calculation. Here, the COM function determines the number of ways to interleave the left and right subarrays. While the theoretical complexity of computing combinations is O, min, A, B, where A and B are the sizes of the subarrays, this is handled as a constant time operation using pre-computed values from the library. Since A plus B always equals N1, this computation is effectively O1. Now, let's consider the recursive calls themselves. The recursion works on the left and right subarrays, and in the worst-case scenario, the recursion depth can reach O(n), such as when the tree is highly skewed. At each level of recursion, there is work proportional to the size of the current array, which includes array splitting and combination computation. Combining these, the recurrence relation for the time complexity is expressed as T(n) equals T, left, plus T, right, plus O(n). In the average case, the array splits into roughly equal halves, resulting in the recurrence T(n) equals 2T(n/2) plus O(n). Using the master theorem, this simplifies to T(n) equals O(n log n). However, in the worst case, when the tree is skewed, the recurrence becomes T(n) equals T(n1) plus O(n), which resolves to T(n) equals O(n squared). Therefore, the time complexity varies depending on the structure of the tree, with the best and average cases being O(n log n, and the worst case being O(n squared). Shifting to space complexity, we start with the recursive stack. The depth of the recursion is determined by the height of the BST formed from the input array. In the best case, where the tree is balanced, the height is O log n. In the worst case, where the tree is skewed, the height becomes O(n). Additionally, at each recursion level, two temporary arrays, left and right, are created as subsets of the input array. The total memory used for these temporary arrays across all recursive calls is proportional to the size of the input array, which is O(n). Combining these observations, the overall space complexity is O(n) in all cases, as the memory usage is dominated by the temporary arrays. The recursion stack contributes O log n in the best case and O(n) in the worst case, but since the temporary arrays also require O(n), the space complexity remains O(n) overall. Finally, let's compare this optimized solution with a brute force approach. A naive method would involve generating all permutations of the input array and checking which ones produce the same BST. This would require O(n) permutations, and verifying each one would take O(n) time, leading to an overall time complexity of O(n)(n). The space complexity for this approach would also be O(n) to store the permutations. In contrast, the optimized solution avoids generating permutations altogether. By directly computing combinations and recursively solving smaller subproblems, the time complexity is reduced to O(n) log n, on average and O(n) squared, in the worst case, while the space complexity is O(n). This demonstrates that the optimized approach is significantly more efficient. By leveraging the mathematical properties of combinations and the structure of BSTs, the solution efficiently determines the number of valid reorderings without unnecessary computations. When solving this problem, there are a few common mistakes to watch out for. First, ignoring edge cases like empty or single-node trees can lead to runtime errors or incorrect outputs. For instance, if the input is an empty list or contains only one element, your code might fail to handle these scenarios properly. To avoid this, make sure to explicitly test your solution with these edge cases and verify that it handles them gracefully. Another frequent issue is misinterpreting the properties of a binary search tree during traversal. Remember, in a BST, all nodes in the left subtree must be smaller than the root, and all nodes in the right subtree must be larger. Failing to enforce these rules can lead to incorrect tree construction or validation. Finally, overlooking duplicate elements can cause problems, as duplicates impact the tree structure and the resulting comparisons. If duplicates are allowed, you need clear rules for their placement, such as always inserting them on the right to maintain consistency. Another common challenge is inefficiently comparing trees by structure. Directly comparing tree nodes one by one can become computationally expensive, especially for larger trees. Instead, you can use serialization techniques like pre-order traversal with placeholders for null nodes. This creates a string representation of the tree, making structural comparisons much faster. Additionally, when dealing with large input sizes, generating all possible permutations becomes infeasible due to factorial time complexity. For example, if the input size is 10, the number of permutations is 10 factorial, which is over 3 million. Instead of generating all permutations, you can leverage the properties of BSTs to prune the search space efficiently. By focusing only on valid insertion orders that maintain the BST structure, you can significantly reduce the computational burden. For interviews, this problem often tests your ability to recognize patterns and optimize solutions. It's a good example of a tree reconstruction problem, so interviewers expect you to demonstrate a solid understanding of BST rules and how permutations affect the tree structure. They also look for your ability to optimize. While brute force methods might work for small cases, they're impractical for larger inputs. Clearly explaining how you analyze and optimize time complexity is key. Additionally, clear communication is critical. If you're unsure about specific constraints or edge cases, don't hesitate to ask for clarification, as thoroughness is highly valued. Before running your code, articulate test cases, including edge cases. For example, consider an empty tree, a single-node tree, or inputs where all elements are identical. Related problems on LeetCode, like generating unique BSTs or reconstructing trees from traversal orders, are excellent practice for building the foundational skills needed to solve this problem. There are also alternative approaches to solving this problem, each with its own trade-offs. One approach is optimized permutation reduction. Since the structure of a BST depends entirely on the order of element insertion, you don't need to generate all permutations. Instead, you can focus on valid insertion orders that lead to the same BST structure. This significantly reduces time complexity but requires a more complex implementation. Another option is using dynamic programming to count permutations that result in identical BSTs without explicitly constructing the trees. While this avoids exhaustive tree construction, it can require additional memory and careful state management. Finally, recursive tree comparison is a simpler approach where you validate whether two trees are identical by their structure and values. However, this method may not scale well for large inputs unless optimizations are applied. Each of these methods provides unique benefits, so you should choose based on the problem constraints and performance requirements. Great job! Let's recap. We tackled the problem number of ways to reorder array to get same BST, explored different approaches, and examined their complexities. Key takeaways include the importance of BSTs, recursion, and combinatorics in solving this problem. Thank you for watching, and don't forget to practice and stay curious. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!